Okay, let's get started. Welcome back. Today is Monday, November 28th. We are covering section 4.3, families of curves. We're also going to have a look at the surge function again, which we looked at during a previous group activity. Today, the data project is due, so whatever you've got, throw it in the folder. If you turn it in late, but by next class, it's 5 points off. If you turn it in after that, it's 10 points off. I only take them up to 1 week late. So turn it in as soon as you can. Coming up on Wednesday, the Rainbow Project is due. And also on Wednesday, we're going to cover something called L'Hopital's rule, and then that's the end of the new material before our test. Friday coming up is our review day. Monday coming up 1 week from today is test number 3. Questions on the calendar? Okay, so like I said, the test is a week from now. It is definitely not too early to start studying. You will find a collection of sample test problems a few pages away in the packet. Okay, so here we are on page 33. In this class, we use calculus to understand the behavior of a family of functions, and we find a member of a family with specified properties. So let's take a look at some specific examples here. Number 1, a formula such as f of x equals ax squared plus bx plus c describes a family of functions. It's just a collection of functions where a, b, and c are different constants. A, b, and c are called parameters, and this family is a 3-parameter family. So imagine all the different parabolas you could get by changing the values of a, b, and c. You could move them left and right. You can move them up and down. You can make them wide or skinny. You could flip them over. The vertex can be moved to any number of spots, right? All the different freedom we have with a, b, and c. So number 2, we're going to find a parabola that passes through the point 1, 4. So first of all, how many parabolas can you imagine that pass through the point 1, 4? Infinitely many, right? Lots and lots of parabolas pass through this one point. But we also want to pick a parabola whose tangent lines at x equals -1 and x equals 5 have slopes 6 and -2, respectively. So one is going to be a positive, from your perspective, +6, and another one like a -2, and it's got to be in exactly those spots, and the parabola is supposed to hit 1, 4. So lots of constraints. We're going to find exactly the parabola that hits all of that meets all those conditions. So let's start with the 1, 4. On the one hand, f of 1 for sure is supposed to be the number 4. But on the other hand, we can find f of 1 by plugging 1 in for all of the x's. So a times 1 squared plus b times 1 plus c. So that means that 4 is equal to a plus b plus c. Okay, so that's one equation that we're going to end up using. Now let's take a look at the tangent line things. We want the slopes to have a certain value. So what should we do with our parabola? Take a derivative, right? Because we're talking about tangent lines here. So let's take a derivative. F prime of x equals. So remember, a, b, and c are constants. Taking derivatives with extra constants floating around is easier when those constants look like numbers as opposed to when they look like parameters here. But still, we treat them like constants. So what's the derivative of ax squared? 2ax plus b. And then the plus c disappears. Okay, apparently we want to know what's happening with this derivative at x equals -1. So let us find f prime of -1 by plugging -1 for the x. So 2a times -1 plus b. But we know what f prime of -1 is supposed to equal. What number is it supposed to equal? It's supposed to equal 6, because it says at x equals -1, the slope is supposed to be 6. So you plug -1 in, but you also make it equal to 6. So that's one equation. 6 is equal to -2a plus b. Just rewriting that previous thing. Can you write the other equation? At x equals 5, the slope is supposed to be -2. -2 equals, you said 5a? Remember, this x is becoming 5. So 10a plus b. Everybody see that? Any questions so far? Which one are you looking at, Ben? this one here to the third one? Yeah. So I ignored the this piece right here. I just didn't bother writing it. So it's 6 equals.
Oh, okay.
Yeah. Okay. All right. So I've now got 3 equations, green, orange, and blue, and I just need to solve my 3 equations for A, B, and C. So the calculus here is done. This is now a matter of solving an algebraic system of equations. So there are a lot of ways to do this. We'll just crunch through it real quick. I see that if I subtract these 2 equations here, the b's cancel, so I'm going to do that. Top equation minus bottom equation, 6 minus negative 2 is 8. Negative 2 minus 10a is negative 12a, and the b's disappear. So that's one way to get us down to one variable. So a is equal to 8 over negative 12, which is negative 2/3. So that's my a. And then we can plug that into, either green or orange to find b. And once we know b, how do we find c? Use blue, right? Okay, so I'm just going to say ... There's nothing else calculus-wise to do. So you just find your values of a, b, and c, and that's it. Questions on the process? Okay, so what we just did was found a member of a particular family of functions. Ax squared plus bx plus c is a whole family. We found the particular member of that family that satisfied certain properties, 3 properties in this case. The group activities, which we're actually going to come back to in just a minute. I'm going to do one more demo thing first. Says find a function of the form at plus b over t. That is a family of functions. How many parameters in that family? 2, capital A and capital B. The only variable here is t. With a local minimum at the point 312. A local minimum at the point 312. So how you set up your equations there is going to be completely different from how we set up our equations. So you just have to think carefully. There isn't one magic way to do all of these. You just have to think about how can I translate the conditions into equations, and then just a matter of solving some system of equations.
Just go back to the beginning. We can talk about, like, x squared and like actually rewrite it as a separate function out of together. Is that like, I'm just so used to seeing a function is f of x or something like that.
Mm-hmm.
So now seeing
You say the inside of the.
Like, I'm not used. I don't know. It just seems weird calling it like family functions, because it just seems like those variables I already know for like a.
Mm-hmm. Yeah. So you could think of that f of x. I mean, that f of x is a function, but because we have the freedom to choose a, b, and c to be any numbers we want, we're going to call it a family, a collection of. And family, like family is a bunch of relatives, like people that have something to do with each other, right? So like any choice you make for A, B, and C, you get a different parabola, but they all have something in common, right? They're all this basic form, ax squared plus bx plus c. So it is one function, but yeah, A, B, and C could be anything. So it's really a collection of functions. Okay. Yeah, Mahendra. We do, and you can do that later. So we found A. You could plug negative 2/3 in for this A right here, and then that would tell you B. And once you know A and B, you can plug them over here, and that would tell you C. Yeah. Okay. So one more problem to do in the demo. Let's try it here on the next page. It says consider this family of functions that you read about in the book. F of x equals negative x minus a squared over b. How many parameters in that family? 2. A and B. A and B are the 2 parameters. E is a constant. E is E. This function is related to a useful tool in statistics called the normal density function. We're going to analyze that same exact function but without the A. And if we can figure out what this thing is doing, what happens when you replace x with x minus a? What does that do to the graph of a function? It's going to shift it either right or left depending on whether a is positive or negative, right? So we're going to ignore the minus a because that's easy. That's just a left or right, and we'll analyze this guy, which is already going to be hard enough by itself. Okay, we're going to assume that b is positive. That will come up later on. So let's give it a shot. First thing we'll do is find end behavior. End behavior means the limit as x goes to infinity of the function e to the negative x squared over b. Okay, so working through this problem is really going to work some math muscles because we've got an extra variable. Think something looks like a variable, that letter b. It's just a constant, but it looks like another variable. So it's just another layer of complexity. So x is really huge. That power is really big, but negative, right? Because b is a positive number. So I've got e to something really huge, negative. E to the negative 100, e to the negative 1,000,000, e to the negative 1,000,000,000. What number is that approaching? It's 0. E to the negative 100 means 1 over e to the 100th power, right? E to the 100th is massive. 1 over that thing is very close to 0. So this limit right here is 0. That was when x went to infinity. But what if x goes to negative infinity? Well, the first thing we're doing is squaring, right? So that's going to take my negative numbers and make them positive. So what's the answer? What's the value of the limit? It's 0. It's exactly the same as it was before because x is getting squared. So that means we can actually say that on both sides, both ends. The graph heads towards 0. Okay, so that's the pre-calculus part. Now we do the calculus part. So we're going to figure out where this function is increasing and where it's decreasing, which means we need to do what with f? Yeah, we need critical points. So what do we need to calculate? Derivative. Let's find the derivative. F prime of x equals. Okay, so this function is e to some stuff. What's the derivative? Good. So e to the stuff, we're just copying all that, times the derivative of the stuff. Okay, you could use the quotient rule. I'm hoping we do not use the quotient rule. That b is a constant multiplier. I mean, it's division, but it's really a 1 over b, right? And that's a constant multiplier. So I'm just going to ignore it. What's the derivative of negative x squared? Negative 2x. What's the derivative of negative x squared over b? Negative 2x over b. Constant multipliers stay. Okay, so there's my derivative. We said we wanted critical points, so we're going to set this equal to 0. E to anything is never equal to 0, so we're going to ignore that. How do I make this other piece equal to 0? X equals 0. That's it. X equals 0 is the only critical point. Armed with our critical point, we're going to make a number line. We're doing a sign chart here. I'm going to pick numbers on either side of 0, plug them into which function, f or f prime? F prime. We're looking for increasing, decreasing here. That's f prime. Okay, so the analysis here can be tricky, but we'll just stick with it. We're picking a number to the right of 0, positive 1. E to anything is always what? Positive or negative? Always positive, right? Imagine the graph of e to the x. It's always above the x-axis. So this guy is for sure a positive number. We said we were picking x equals 1. So that means the numerator is how much? Negative 2. Yeah? We are assuming throughout that b is a positive thing. That was up there in the givens. So what is the sign of this fraction? it is negative. So with a lot of talk and hardly anything written, we put a minus sign right there. Don't shortchange that analysis. You really have to go piece by piece and make sure you get the right sign. Okay, now we're going to pick something to the left of 0, -1. What do we think about E? Always positive. How about the numerator here when x is -1? That's positive, divided by a positive number B, positive. And so now we can make our conclusions here. That means that to the left of 0, what is f doing? Decreasing or increasing? It's increasing. And to the right of 0, negative derivative means f is decreasing, which makes 0 a what? Min or max? Max, right? Increasing and then decreasing. Great. Feels like we should also know what f of 0 is so we can actually plot that point. So what do we get when we plug 0 into f? E to the -0 squared over b. That whole power is what number? 0. So e to the 0 is 1. E to the 0 is 1. Okay. So 0, 1. That's a maximum. And it's not just a local max, because this function is increasing forever to the left of 0 and then decreasing forever. So it is going up all the time until it gets to 0 and then is going down all the time. So an absolute maximum at x equals 0. Okay, so I think we finished everything with the first derivative. What information are we going to get from the second derivative? Cavity. Let's try it. F double prime of x equals. Okay, to take a derivative here, what rule? That is a product. There's no getting around it. You got x's times x's. So let's use the product rule. So first times derivative of the second. First times the derivative of the second. Again, you could use the quotient rule, but I'm hoping we don't. -2 over b is the answer. That's it. This whole thing right here is a constant times x. Yeah? So the derivative of that is just the constant, -2 over b. Okay, -2 over b. All right, so we're in the middle of the product rule here. That was first times derivative of the second plus second. So copy the -2x over b times the derivative of the first, which is that blue thing that we wrote before. So I'm copying the entire blue thing now. So that was second times derivative of the first. Several people recognize right away we'd already done the derivative of the first, so we just copied it. Okay, we're going to take this second derivative and set it equal to what magic number? 0, looking for places where the concavity changes. Second derivative is supposed to change sign. So it's in our best interest to simplify as much as possible. That means factoring out. What can we factor out of both? There's a plus sign in the middle. What can we factor out of both? E to the -x squared over b is definitely coming out. Yeah, so we can't take out the x because this first guy doesn't have the x, but we can take out -2 over b. So let's do that. Okay, what's left for this first term once we factor it out? One. We factored everything out, so kind of like nothing, but we do have to have that placeholder of a 1. Okay, next up, I factored out the e part. I'm going to try to circle what's already outside. So that is outside, and -2 over b is outside, but everything that I didn't circle is still here. So what I think I see is a negative there, an x there, and another x over here. I think that makes 2x squared over b, and that's it. So make sure you see how to figure out what's left in those parentheses. So there was a solitary x sitting in the first thing that didn't quite get circled, and that's where the x squared comes from. Multiply. Yeah, but not the x over b, just the x. The b is factored outside. So that x times this -2x is where the -2x squared comes from. So that's the x squared, and then there's a single b here, not b times b, but just a single b. Okay, I think that's as good as it's going to get. Again, we said we're going to take the second derivative and set it equal to 0. And because we spent that time putting the second derivative into factored form, solving this equation is pretty easy. What do you think about e ever equal to 0? No, we can ignore it. How about that fraction, -2 over b? Is that ever equal to 0? No, doesn't even have any x's in it. That's a constant. So really all we need is the parentheses equal to 0. So let's try that. 1 minus 2x squared over b, setting it equal to 0, and solving this for the only variable there, which is x. All right, so I'm going to add that fraction to both sides. I like my things to be positive if I can make them positive. We're going to multiply both sides by b over 2. And then take the square root. How many solutions does this equation have? Should have 2, right? Because why? Because of the square, right? Whatever that highest power is, that's how many solutions you have. Troy? Yeah, it's really easy to forget. When we take the square root, we got to put in the plus or minus. Okay, so I think we're good there. We are going to do another sign chart. I've got negative root b over 2 and positive root b over 2. And I want to label this sign chart. Is it f, f prime, or f double prime? F double prime. Label it with whatever function gave you the zeros. In this case, it was the second derivative equal to 0. That's where those radical numbers came from. So we're plugging into the second derivative. Okay, so we're picking something. Let's pick something way out to the right, something massive, much bigger than square root of b over 2. So when we do that, plugging into the second derivative, x is supposed to be enormous in this case, right? So I've got -2x squared. So that's really, well, 2x squared is this really enormous thing. B is a positive number. So this whole thing is what kind of a number? Is that positive or negative? There's just this piece right here. That's a positive. And it's supposed to be really big. And then I'm doing 1 minus this really big number. And so this thing is negative. Okay, so I'm going to put this and then I'm going to erase it. But that's supposed to be a negative right there. E is always what? Positive. -2 over b is always negative because b was a positive number. That's what we assumed. So the whole thing is positive. So down here, we've discovered this thing is positive. Okay, let's skip to the far left of that number line. X was really huge and positive. Now we're going to make X like also positive, also really huge but negative. But the first thing we do is square it, right? So what's going to be our answer at the far left of this number line? It's going to be the same answer we got at the far right, right? Because we square X. So plugging in a huge negative is the same exact thing as plugging in a huge positive. So that's just a copy of the work we did before. So the only question is what's going on in the middle. Fortunately for us, there's a really easy number that is definitely in the middle, 0. But you can't pick any other number besides 0. If you try to pick like 1, well, if b is a really small number, like really close to 0, then 1 will be on the wrong side. So you got to make sure you pick something that's definitely between. So in this case, we're plugging 0 for x. So when we plug 0 for x, this piece right here, 1 minus nothing is positive 1. E is always positive. Negative 2 over b is a negative thing. So the whole thing is negative. So that's what goes in between. All right, let's write our conclusions. Out here, F is concave up. In between, concave down. And to the right, concave up. We're going to do a quick sketch here of F, and then we'll look at Sketchpad, and then you'll do the demo or the activities. Okay, we discovered earlier that the point 0, 1 was a maximum, right? Because the function was increasing until we got there and then decreasing after. And we also discovered that to the far right and the far left, the function is heading towards 0, meaning it's getting close to the x-axis. So that means that it's something like that and that. And so I'm just going to connect this the only way that I can. And the only question is, what haven't I labeled yet that's important about that graph? Inflection points. And we found the inflection points. They're at negative root b over 2 and root b over 2. I can't really say anything specific about them. I'll just kind of generally say this is out here somewhere, and then this is the mirror image. Negative root b over 2. But that's it. That's exactly where the inflection points are. And notice that I drew this thing without thinking about the concavity. I just said, hey, it's got to get close to the x-axis, and it's got to be increasing and then decreasing. But does the concavity match with what? Yeah, it's concave up, and then concave down in the middle, and then concave up again. Okay, so one quick look at Sketchpad here. So this thing is the original function. At the moment, I've got a equal to 0, so we can ignore that part. And b is equal to 1 right now. And so if b is equal to 1, that means my inflection points are at root 1/2 and negative root 1/2, just with b equal to 1. And so that is here. Root 1/2 is 0.71 and negative 0.71. Concave up, concave down, concave up, increasing until 0 and decreasing the rest of the way. And if I take b and make it bigger, you can see what happens to the location of the inflection points. They just get farther away from the origin. That's fine. What is a little bit surprising is that what can you say about the y value for those inflection points? It never changes, which is not something we discovered. But if we plugged in root b over 2 into the original function way back here, we would discover that it has no b's in it at all. It's just the same number all the time. So it doesn't matter what b is, but the inflection points stay exactly at the same height. That's kind of cool. And then the only other thing was that we could take a and shift this guy left and right. We ignored that part of the analysis, but that's what it looks like. And so you guys have seen this bell-shaped curve before, right? Like a lot of distributions follow this. Like if you Wanted to think about the height of people here in the US. Whatever the average height is, let's call it right here in the middle. And then you got some people that are taller than average and some people that are smaller than average. Most people are going to be right inside of here, but you will have some really tall people here and then some NBA players over here. And then you'll have the other extremes for people that are a little shorter than average and then a lot shorter than average, but hardly anybody, you know, like really far from the middle. So that's what's going on here. A lot of examples follow this bell-shaped curve. Okay. All right. So what you're going to do for the activity, you're going to go back, do this problem right here on the previous page, number 4, and then you're going to go past the one we just did and do the surge stuff.